So thank you very much for this very beautiful introduction. So I'm going to talk about a very special case of tinnitus. If you take an average neuroscience textbooks, you'll see that it's filled with special cases. I hope to convince you here that also this might be an interesting case that might actually tell you something about tinnitus in general. Of course, because that's of course what we're hoping to achieve. So what I would like to do is first give you a little bit of background about tinnitus. What is tinnitus? Why would we care? And then I would like to tell you about one experiment we did in this very special group of tinnitus patients that can actually modulate their tinnitus by gazing with their eyes. Very exotic observation. So tinnitus is a sound that people hear while there's no sound present in the environment. Typically people describe it as a tone or a noise. It can have various characteristics. I thought it would be nice to actually have you listen to a tinnitus sound. Well, in the sense that it's impossible because you cannot record tinnitus. There's a small group where you can actually record a sound. That's called objective tinnitus. So you can actually record a sound coming out of the ear that's apparently corresponding to a percept people have. That's typically related to some sort of aberrant vessel that produces a sound. But in the vast majority of people, you cannot record the sound and there's no sound to be found. So the percept that people have must be based solely on neural activity of eventually auditory neurons in the brain. But fortunately, there are of course always some technical people that are able to reconstruct their own tinnitus by using some sort of digital synthesizer. If you go onto YouTube, you'll find many examples that say, this is how my tinnitus sounds. And you'll find quite a range of sounds that people actually say they hear. But the example I have here is, I have to move out this very briefly. The example I have here is sort of characteristic in that many people describe hearing a high-pitched sound. So this was also from YouTube. So this is the kind of sound that people describe hearing, well, basically all day, all night. If they're awake, they may awake due to the tinnitus, hear the sound and be unable to get back to sleep. They hear it the entire day, and obviously it's not fun, I guess. Maybe you want me to turn it off again. I could leave it on, because actually, besides the fact that the sound is there, it also hinders you in your communication, obviously, because it's in the way. So but I'll help you here. You will be the first people we are actually able to cure. So tinnitus has many consequences. Apart from the fact that people hear this sound, they have problems in concentrating, lack of sleep. Obviously, the sound can keep you awake. In some people, it's a complete showstopper. They are absolutely unable to participate in society, to go to their work and do their daily activities. And it leads to anxiety and depression in a number of people. So these are all quite far-fetching psychological consequences. And if I tell you that we don't really have a good therapy to cure tinnitus at the moment, I think you can imagine that a psychologist in our team plays an important role, because the psychological treatments for the consequences of tinnitus are in fact quite effective. Not for curing tinnitus, but at least for dealing with it. The prevalence of tinnitus is amazing. This is a number from a recent study in the Netherlands. Although of course the Netherlands is only a small country, I thought it was a good study, so I quote the study here. About 10% of people say they hear tinnitus, and about 4% say that they hear they are severely hindered by their tinnitus. So that's a severe number of people. 650,000 people in the Netherlands, about 30 million in Europe. Now these prevalence numbers are always tricky, but some prevalence reports go up to 20% of people. Some prevalence reports on severe tinnitus go down to 1% of the people, but even if 1% of the population is hindered by severe tinnitus, it's a serious problem to deal with. This study also computed what in the Netherlands are the cost of tinnitus, and that's 6.8 billion euros per year that the Dutch society spends on tinnitus. That's mostly societal cost. Well, there's no cure, so you can go to the doctor, but the cost will be relatively small. But it's mostly due to missing out of work and that sort of things, that the costs are 6.8 billion euros. Now, I can do this here, right? It has been our focus not to think about the cost or whatever, but to try and understand what the physiology of this condition is. Why does it happen? Why do people hear tinnitus in the first place? Well, one first thing that is immediately apparent is that it's closely related to hearing loss. So people that have a peripheral hearing loss, they often describe hearing tinnitus. About 30% of the people with hearing loss will describe hearing tinnitus. And although it's an ear problem, we also come to realize that the brain plays a key role in the development of tinnitus. And that's already known for quite some time. For example, surgeons know that if you cut the auditory nerve, which is necessary in some tumor surgery, that after cutting the nerve, people may actually develop tinnitus. So you don't even need an ear to get tinnitus. Just having a brain not connected to the ear is sufficient and you can get tinnitus. Yet there's a strong relation to hearing loss, and that has been studied quite extensively in animal models of tinnitus. Obviously, any percept must involve neural activity, and this particular slide shows you the effect of noise trauma, which is known to cause tinnitus in humans, the effect of noise trauma on neural activity in a number of auditory brain centers. And this is all animal research. It's projected on a human brain, as you can see, but it's all animal studies, I think in cats and rats. Now, if you traumatize the ear with sound, so it's an interesting trauma because the only trauma is in the ear, and yet you find all these consequences in the brain. But if you traumatize the ear, it turns out that activity in the auditory nerve really goes down substantially, almost to zero. And we're talking about spontaneous neural activity here. So if this goes down to zero, you would expect it to become really silent, right? There should not be any sound. But it turns out that in several brain areas, actually the spontaneous activity goes up, is upregulated. So you could imagine that such activity that's measured in lab animals could actually correspond to tinnitus. Now, of course, we don't know for sure whether these animals hear tinnitus, but there are techniques, behavioral techniques, to try and figure out whether an animal might hear tinnitus. And indeed, animals showing this type of increase of activity seem to hear tinnitus. In fact, this is actually one of the motivations for an important treatment that we try, and that's, for example, to provide hearing aids to people with tinnitus. If you think it's a result of hearing loss, then you could try to restore hearing as good as you can, and then you have a good chance that the tinnitus will actually go away or get less. And a portion of people, I would say about 40%, actually say that if you give hearing aids, that the tinnitus goes down substantially, even to going away entirely. Also, deaf patients, we give cochlear implants for deaf patients, and also deaf patients have tinnitus very often, and a large portion of these patients say that their tinnitus decreases substantially after getting the implant. There's also an interesting parallel to phantom pain sensations. I'm sure you know the fact that if you miss a finger, you might feel pain or tinkling or whatever in the finger that you're actually missing. Well, something similar, this is similar to that. If you have, for example, your auditory system detects a range of frequencies, and if you miss a couple of frequencies, typically the high frequencies, then it turns out that also at the frequencies that you miss, you start hearing the tinnitus. So there's a very interesting correspondence to neuropathic pain. Now, this is all animal research, and of course we like to somehow take these results to humans and try and detect in humans what sort of brain activity actually corresponds to tinnitus. Well, the techniques we've been using, the technique we've been using so far is functional magnetic resonance imaging. That's of course a great technique for localizing brain activity. For example, in response to a stimulus, for example, in response to sound. And this particular example is showing you responses to a sound stimulus in normal hearing people. Now, it's great for detecting changes. I mean, for example, detecting what the brain looks like if there's no stimulus to what the brain looks like if there is a stimulus. In such a paradigm, you can use this technique very actively. Of course, in tinnitus, the tinnitus is always there. So ideally, you would have subjects that can actually switch off their tinnitus, and now we make a scan, and then they switch it on again, and we make the next scan. Of course, that's not possible, but indeed there are some people that can modulate their tinnitus, and they have been, and that's one group of those is the people with this gaze-evoked tinnitus. So those people we put in the scanner and we try to detect what brain activity actually corresponds to tinnitus. If their tinnitus goes up, what sort of brain activity do we find? So this gaze-evoked tinnitus, or actually I should maybe say gaze-modulated tinnitus, because people have tinnitus which modulates by eye gaze. It's very rare, but it's relatively common in patients that underwent acoustic neuroma surgery. The acoustic neuroma is a neuroma on the 8th cranial nerve, and treating that tumor sometimes involves also cutting the nerve. And about 36 to 19% of patients that have this say that eye gaze changes their tinnitus. So these people are deaf in one ear, the ear in which they hear tinnitus. They are deaf after the surgery. They have the tinnitus in this ear, and they can modulate it by eye gaze. Interestingly, the first description was by Whittaker, who had a patient that came to him and said, if I drive my car and I look in the mirror, I hear a tone. Well, I guess Whittaker was sort of surprised initially, but then he found out, of course, that more patients describe similar effects. So what do we find is first of all, one example, one advantage, if you may call it, of this patient group is that they may have one deaf ear with tinnitus, but they also have one normal hearing ear. So you can present sounds to the normal hearing ear and ask them, patients to match that sound with whatever tinnitus they hear. So you can map out quite nicely what people actually hear, what frequencies they hear, what loudness they hear this at, etc. So that's what we did. It's a long experiment, very tiring for the people, for the patients that it involves. But we asked patients, for example, how does loudness change, the loudness of the tinnitus change with eye gaze? And then 11 of the 18 patients that we investigated say that gazing actually increases their tinnitus. Interestingly, in the same group of people, there are also people that say that tinnitus decreases with eye gaze. And some said that the loudness is equal, although some other sound characteristic actually changes of the tinnitus. Now, we were not so much interested in exactly why this phenomenon happened. We just used this patient group to investigate the relation between loudness and brain activity. And I'm going to show you some results, and what I'll show you is a so-called region of interest analysis. I'll show you the changes of brain activity in the inferior colliculus in the brainstem, in the medial geniculate body in the thalamus, and in the auditory cortex on the temporal lobe. So just average responses of these areas. And this is what we essentially find with increasing tinnitus. We find that that activity in the inferior colliculus increases if people say that the loudness of their tinnitus increases. The same happens in the auditory cortex. We find that activity increases if their tinnitus increases. These responses are very normal for sound. With every external sound we present, we find that, that the MRI signal increases. However, in the medial geniculate body, in the thalamus, we find a decrease of the activity. And this is completely unexpected and really very abnormal. So at present, we think that the thalamus must play a key role in tinnitus in some way or the other. It's actually consistent with some results we had before, where we found that functional connectivity between brain and cortex is abnormal in tinnitus patients. This result, maybe the first thing I should say about it is that it's also important for tinnitus patients. The fact that we now have an objective measure of something that was previously called a subjective complaints because you couldn't measure it. Now for us all here in this room, it's probably very trivial that you'll find this sort of brain activity, but for tinnitus patients it's actually very important to know that what they hear corresponds to something that actually happens in their body. And of course they say, they might initially say, I'm always hoping that it's not between my ears, as they say, but actually it is between their ears, of course, but in a different way than it was initially meant. One interesting aspect is the correspondence to neuropathic pain. Also, there are many imaging studies of neuropathic pain. And I guess like in the tinnitus field, also the neuropathic pain MRI studies are very diverse in their outcome. But there's one single consistent result in neuropathic pain imaging studies, and that's the neuropathic pain also corresponds to inhibition in the thalamus. So there seems to be in this sort of conditions, there seems to be something special about the thalamus. So maybe as a last remark on this result, obviously we need to do a lot here. We need to expand this study to other groups of patients to see whether this is indeed a consistent result. But you could slowly start thinking about what sort of therapy would be helpful. I guess if eventually we are able to do local application of drugs, you could imagine that you could apply it somewhere deep in the brain at the thalamus, if that's indeed the key structure in the brain that's involved in tinnitus. Also, you could think about future deep brain stimulation approaches. That might maybe one future neuromodulation technique which is going to be helpful. Although neuromodulation, of course, doesn't necessarily need to be done at the location where the problem is. For example, I guess you could call fitting a hearing aid already a form of neuromodulation because you're changing brain activity, and obviously you do that far in the periphery and it might still help causing tinnitus. So with this I hope to have shown that this special case actually might tell you something about tinnitus, and we hope of course to make this broader in the future, and I think that it will also direct us to being able to develop treatments for this condition. Thank you very much.